Hi folks, so today what we're going to be looking at are the solutions to the 2018 Exploring Physics OCR Physics A past paper. If you guys are looking for the multiple choice solutions, they're in a separate video and I've included a link in the description just below this video. Okay, well, let's get started. Question 16, derive the SI base units for resistance. So the formula for resistance is V divided by I. So all we need to do is find out the base units of V, and I is already in base units, so that's the amps. So let's start finding the base units for V. So V is energy per unit charge, W over Q, which is also equal to W divided by IT, because charge is current times time. Now the base units for work done or energy are equal to kilograms meters squared S to the power of -2. How do I know that? If you can't remember that, you can just quickly write on the side a formula for energy, for example, half mv squared, and this will have units of kilograms meters per second raised to the power of 2, which is going to give us this expression. Okay, so it's energy per unit charge, so it's going to be energy per amps seconds. And if we were to just write this as a single line, this will be kilograms meters squared amps to the power of -1 s. So I have s to the power of -2 divided by s again, which is going to give me s to the power of -3. Now these are the base units for potential difference. In order to find the potential difference, the units for the base units for resistance, I need to divide by amps yet again. So these were just the base units for potential difference. So the units, let's write this down, the units for R are going to be kilograms meters squared A minus 1 S to the power of -3 divided by the units of current once again, which is going to give us base units of kilograms meters squared amps to the power of -2 S to the power of -3. Okay, next one, show that the resistance of R is 40 ohms, where R is a resistor. Okay, well, R is equal to V over I, so all I'm going to need are two values, one for the potential difference and one for the current. Let's pick this one over here. So we can see that the voltage is going to be 6 volts, and the corresponding electrical current will be 150 milliamps. So I'm going to divide the 6 volts by 150 milliamps. Let's not forget this bit, that's really important. That's going to cost us the mark otherwise. So it's going to be 6 divided by 150 times 10 to the power of -3, which if we put into a scientific calculator, we are going to get 40 ohms. Okay folks, so let's have a look at the next one, which is part 2. In this case we have the lamp and the resistor, which have been connected in series to a battery. Use figure 16.1, which is this figure over here, to determine the internal resistance R of the battery. Now in order to find out the internal resistance R, I'm going to need to find the total resistance in the circuit. I know that the current is 100 milliamps, so I will be using the fact that my EMF, which is also given in the question as 6 volts, is going to equal to the current times R, where R is the total resistance in the circuit plus the internal resistance. So I know what this is in the question. This is just 6 volts that's given. I know that the current is 100 milliamps. I don't know my total resistance just yet, but if I do, I'll be able to rearrange this expression for the internal resistance. Okay, well, let's get started. This is a series circuit. The total resistance of the circuit, discounting the internal resistance, of course, is going to equal to the resistance of the lamp plus the resistance of the resistor R. So let's work them out separately. At 100 milliamps, right over here we can see that the potential difference is 1.4 for the lamps, 1.4 volts for the lamps. So RL is going to be equal to V over I. So this will be 1.4 over 100 milliamps, which is equal to 0.1, which is going to give us 14 ohms. The resistance across, or the resistance of the resistor R, this is going to be the potential difference across it, and at 100 milliamps, which is the current in the circuit at the time, so at 100 milliamps, the resistance is 4 volts. So, sorry, the potential difference is 4 volts, 4.0 volts. So we're going to have 4.0 divided by 0.1, which is going to give us 40 ohms. So it means that our total resistance in the circuit, RL plus RR, is going to be 54 ohms. So that's the resistance of this one plus the resistance of the resistor at 100 milliamps. Now we can work out our internal resistance pretty easily. We know that our EMF is 6.0 volts. We know that our current is 100 milliamps, which is 100 times 10 to the power minus 3, which is equal to 0.1. We know that our total resistance in the circuit is 54 ohms, and we have an equation with just one unknown. So I'm going to divide both sides by 0.1, which is going to give me that 60 ohms is equal to 54 plus R, meaning that R is going to be equal to 6 ohms. Okay, folks, so for the next one, we need to calculate the resistivity of the material of the resistor R. Our formula for resistivity is equal to R multiplied by the cross-sectional area divided by the length. Now, this is the resistivity of the resistor only, so we need to not get confused on this. The resistance of this is calculated above here, and that's 40 ohms. We have the cross-sectional area when we also have the length as well. So let's plug in these numbers. The resistance is 40 ohms. Our cross-sectional area is equal to 2.4 times 10 to the power of minus 6 meters squared, and we're going to divide that by the length, which is equal to 8 millimeters, or 8.0 times 10 to the power of minus 3. If we put this into a scientific calculator, we're going to get 0.012 ohm meters. Okay, folks, now for the next one, there are 6.5 times 10 to the power of 17 charge carriers within the volume of R. Calculate the mean drift velocity. Okay, now in order to calculate the mean drift velocity, we're going to need our number density. And we'll need to remember that our number density is equal to the number of charge carriers per unit volume. In other words, n, the number density, will be equal to n, the number of charge carriers, divided by the overall volume. So our number of charge carriers is 6.5 times 10 to the power of 17. We're going to need to divide that by the volume. We're given the length of the cylinder and the cross-sectional area of the cylinder, so we can work the volume out from there, keeping in mind that the length is given in millimeters and the area is given in meters squared. So we're going to need to convert the length to meters, which will be 8.0 times 10 to the power of minus 3 times 2.4 times 10 to the power of minus 6, like so. And if we put that into a scientific calculator, we're going to get 3.39 times 10 to the power of 25. This over here is our number density. Now we can use the equation for the current and the drift velocity to work out our drift velocity. So we know that I is equal to number density times cross-sectional area times the elementary charge times the drift velocity. I'm going to rearrange this for V, which will be I divided by NAE. Now in this case, our current is 100 milliamps, so that's 0.1 amps. I'm going to need to divide that by our number density, which is 3.39 times 10 to the power of 25 times our cross-sectional area, which is equal to 2.4 times 10 to the power of 6, 2.4 times 10 to the power of 6, like so. I'm going to need to multiply by the electron charge, which is 1.6 times 10 to the power of minus 19. And up to two significant figures, our final answer for this one will be 7.7 times 10 to the power of minus 3 meters per second. Okay folks, so let's have a look at question 17. We have a potential divider circuit which is connected to this device which spins a metal plate, and every time the hole passes above the LDR, this will affect the resistance of the LDR. Essentially, this potential divider circuit will just be a standard one, just like in any question. The first question is asking us to explain the shape of this graph. Now this shows the variation of the potential difference V across the fixed resistor. So it's this bit, the voltage across the 1.2 kilo ohm fixed resistor, that is being plotted. Our first job will be to just explain the shape of this graph. It's obvious that we have some spikes in potential difference, and let's see whether we can explain it. Now I've actually pre-written a little answer over here just on that first part. So let's have a look at it. Notice that one thing I've done is I've just underlined all the bits that I need to do in this 6-mark question so that I don't forget any of them. So I'm going to need to use my understanding of potential divider circuits to explain the shape of the graph shown in figure 17.2. Then we're going to do some calculations on the maximum and the minimum values of the resistance of the LDR. And finally, we're going to calculate the frequency of the rotating plate. So let's focus on the shape of the graph first of all. Okay, well, notice how in my pre-written explanation of this graph, I've actually labeled the first bit, shape of the graph explanation. This is essentially to make my work a little bit more organized and to let the examiner know that in this section over here, I am going to be talking about the shape of the graph, which is one of the first things that they have asked me to discuss. Okay, well, what actually causes these spikes? As the plate spins, light will be going through the hole and then onto the LDR periodically. This will change the resistance of the LDR, which in turn will change the potential difference across this fixed resistor, which is where this data logger is connected to. So in other words, the increase and decrease in PD is due to light going through the hole onto the LDR periodically. Now let's have a look at how does our knowledge of potential divider circuits have an impact on this. So first of all, as light goes onto the LDR, the resistance of the LDR decreases. Remember, this is one of the most important graphs that we need to remember for our A-level physics, particularly this paper. So the resistance against light intensity, so let's write light intensity for an LDR looks something like this. In other words, as the light intensity increases and light shines from the lamp through the hole onto the LDR, the resistance will be decreasing. Now, because the resistance of the LDR decreases, that means that the entire resistance, the total resistance in the circuit, will be decreasing, because this is just a fixed resistor, this doesn't change. So if the resistance of the LDR decreases, then also the current in the circuit must increase. So this is really, really important. This is simply because current is inversely proportional to resistance. Now here's where it gets a little bit tricky. If the current in the circuit increases, so if the current in the circuit increases, then the potential difference across this fixed resistor should also increase. And this is because of Ohm's law, because V is equal to IR. Remember, in this case, R is fixed, it's 1.2 kilo ohms, which means that the potential difference across the fixed resistor must increase. And this is what is actually causing the spikes. Every time light goes through the hole onto the LDR, the resistance of the LDR decreases, which increases the current in the circuit, which increases the potential difference across the fixed resistor, leading to those spikes. And the way I've explained this over here is light intensity increases, the resistance of the LDR decreases, and the current in the circuit increases. The PD across the fixed resistor will then increase as V is equal to IR. R is fixed, it's 1.2 kilo ohms, and I increases. And this actually accounts for the spike in potential difference shown in the graph. It's important to note as well that the actual PD across the LDR will be decreasing, and that's because of Kirchhoff's second law, that the sum of those PDs have to add up to the fixed value of the EMF. So if this one increases, then the one across the LDR must decrease. Okay, so we've done the first bit. Now let's see whether we can calculate the maximum and minimum values of the resistance of the LDR. Okay, now let's start off with our calculations. So I'm just going to write over here calculations, and I'm going to start off with the calculation when the LDR is in the light. I'm going to use my potential divider equation. You could do it using either equations, but I'm just going to use the fact that V1 over V2 is equal to R1 over R2, and this equation is given in your formula booklet. Remember, V1 is the potential difference across one of the components. Let's say that in this case V1 will be the potential difference across the fixed resistor. So let's say that when it's in the light, the potential difference across it is 4. So we can write this in, so 4 volts, and the resistance corresponding to this component is 1.2 kilo ohms, which is 1200 ohms, like so. Now, if the potential difference across the fixed resistor is 4.0 volts, then that leaves 0.5 volts for the potential difference across the LDR, which is our V2. So this is going to be 0.5. We're going to need to divide that by R2, which is the resistance of our second component, which in this case is the LDR. So we can just rearrange for R2 in this case, and R2 will be 1200 times 0.5 divided by 4, which, if we put into a scientific calculator, is going to give us 150 ohms. Okay folks, now we're just going to repeat exactly the same calculation when there's no light on the LDR. In other words, we're going to be in those regions over here, which are the flat regions on this graph. I'm going to use exactly the same equation, that V1 over V2 is equal to R1 over R2. Okay, well, our potential difference across the fixed resistor is now 2 volts. So this will be, our V1 will be 2.0 volts, not 20. Let's make sure that the dot is visible. And this is going to equal to the resistance, which is fixed across the fixed resistor. That's still 1200. Now, if there's 2 volts used up by the fixed resistor, that means that there will be 2.5 volts left for the LDR, because they need to add up to 4.5. So I'm going to divide that by 2.5, and I'm going to have R2 like so. Okay, well, in this case, all I need to do is just rearrange for R2, and R2 will be equal to 1200 times 2.5. I'm going to need to divide that number by 2, and this will give me 1500 ohms, like so. We are almost done with this question. The final bit that we need to do is to describe how the student can determine the frequency of the rotating plate. So this is the final bit that we're going to do. I'm just going to label that bit determining the frequency. So determining the frequency. Now the first bit that we will be doing would be just to obtain the time period from the graph. So obtain the time period from the graph, the time period from the graph. Now the easiest way to obtain the time period is to just pick a point. So let's say this point over here, which is 0.2 seconds. So this one here will be 0.2, and it will be the distance to the next time the cycle repeats itself, which will be at 0.6 over here. So this distance there is actually 0.4 seconds, and this is our time period. So we can just say that this is equal to 0.4 seconds. Now after we have our time period, we can then determine the frequency of oscillation by just doing 1 over the time period. So the frequency is 1 over the time period, which is equal to 1 over 0.4, and this will give us 2.5 hertz. So 2.5 hertz. Okay, so we've done pretty much everything that's been asked from us. So we have explained the shape of the graph successfully. We have included the answers for the maximum and minimum values of the resistance of the LDR, and we've also found and describe how the student can determine the frequency of the rotating plate. Okay folks, so question 18. Show that the angle theta between the refracted ray in the glass and the reflected ray in the air is 90 degrees. Okay, well, for this one it's also important to realize that we're going to need to be applying Snell's law, which is that n1 sine theta 1, so n1 sine theta 1 is equal to n2 sine theta 2. Now in this equation, which I've written down, n1 in this case will be the air, so it's going to be 1. Sine theta 1 is the sine of this angle over here, and n2 is going to be the refractive index of the glass, like so, and we can use that to determine the angle of refraction, which is theta 2. Now theta 2 is this angle over here, which I have which I'm just shading over here now. So this is not the angle that we're looking for, however it will be used afterwards, so that's really important to notice. Okay, now let's start plugging in some numbers into this equation. So n1, as I said, is just equal to 1, so I'm not even going to write that down. I'm going to write that the sine of theta 1, which is 56.3, is going to equal to the refractive index of this glass, which we're given here, which is 1.5. So 1.5 times the sine of this angle theta 2, and I can just rearrange for the sine of this angle. So sine of theta 2 is equal to the sine of 56.3 divided by 1.5. And I can just use the inverse sine function of my calculator to find out the angle theta 2. So theta 2 will be the inverse sine of this expression. So sine of 56.3 divided by 1.5. And if we put that into our calculators, we're going to get that the angle of refraction, theta 2, will be equal to 34 degrees or 33.7 degrees, to 3 significant figures in this case. Okay, now I can apply just simple addition of angles to figure out what this angle over here is. Now all of these angles across this side are going to add up to 180 degrees. So I know that this angle over here is also going to be 56.3. How do I know that? The angle of incidence is always equal to the angle of reflection anytime we're dealing with the reflection of light rays. So I'm just going to say that 56.3 degrees plus the angle that I'm looking for, called theta, plus this angle that we just found out, 33.7, plus 33.7 degrees are going to equal to 180 degrees. So theta will be 180 minus 56.3 minus 33.7 degrees, and this is equal to 90 degrees. Okay folks, next one, describe how you can demonstrate in the lab that the reflected light is plane polarized. So we need to take a polarizing filter and we need to place it in the way of or we need to look at the reflected ray through the polarizing filter. So I'm just going to say that for the first point we need to use a polarizing filter. And additionally, what we must definitely do is to rotate that polarizing filter. So rotate the polarizing filter. This is really, really important. Now, if the intensity of the light changes, that means that the light is plane polarized. So then what we're going to say is if the intensity of the light changes, it is plane polarized. Okay, on to the next one. So for part D, we need to calculate the time taken for the refracted light to travel a depth of 6 centimeters through the glass. Now there is a catch to this question, so I think it's a really, really good idea to actually draw this. Now the refracted ray is not moving vertically, it's moving at an angle. So the depth is going to be given by this length over here. Let's use red for this one. It's going to be given by this length, like so. Now this length in this case will be equal to 6, like so. So we're going to need to use the cosine function to actually figure out what our distance d is, which will be the hypotenuse in a triangle such as this one. So in order to work out our distance, I've just called that d. We're going to need to just use the cosine function. So the cosine of let's go back to using the black pen just like in the exam. So the cosine of 33.7 degrees is equal to the adjacent over the hypotenuse. So our adjacent is 6, and our hypotenuse in this case is what we're looking for. I've just called that d. So we're just going to rearrange for d. D will be 6 divided by the cosine of 33.7 degrees, which if we put that into a calculator, we're going to get about 7.2 centimeters. So now that we know that the distance the light ray has to travel to achieve a depth of 6 centimeters, which is 7.2 centimeters, we can work out the actual time just using the fact that the distance is equal to the speed of light multiplied by the time. And we can just essentially rearrange for the time. So the time will be equal to the distance divided by the speed of light. The distance in this case is 7.2 centimeters. Let's not forget to convert that into meters. So it's going to be 7.2 times 10 to the power of minus 2 divided by the speed of light, which is 3.0 times 10 to the power of 8. And if we plug that into a scientific calculator up to two significant figures, we are going to get 3.6 times 10 to the power of minus 10. Whoa, that's a pretty small time. Okay, right, let's go on to the next one. Okay, question 19. Figure 19.1 shows the image of an experiment using a ripple tank. State two-way phenomena or properties that can be observed in this image. You may annotate the figure to support your answer. Well, first of all, just over here we can definitely see some evidence of diffraction, that is the spreading of the waves as they go through an opening or around the edge of an object, which is clearly visible over here. So one of them is diffraction, so let's write that down, diffraction. Additionally, we can also see maxima and points of maximum and minimum intensity as well. So we can clearly see that there's evidence of interference. Okay, next part. Okay, next one, which is part B. We have two transmitters, A and B. They emit coherent microwaves in all directions. A receiver is moved at a constant speed along the line from P to point Q, which is parallel to a line joining the two transmitters. Explain why the output signal from the receiver fluctuates between minima and maxima. Okay, well, this is clear evidence of interference occurring. So we can just write this down, that the signal fluctuates due to interference. Now, every time there is a maximum, a crest will meet a crest, which will cause the signal to be a maximum, and this will be an example of constructive interference. So when constructive interference occurs, the signal is at maximum. And on the other hand, when destructive interference occurs, in other words, a crest meets a trough, the signal will be at a minimum. So when destructive interference occurs, the signal is at a minimum. Okay, let's have a look at the next one. Okay, so question 20, this is all about the LED experiment to determine Planck's constant. Now, I have a dedicated video on this experiment, so if you're not quite so happy with this question as well, especially after watching this video, have a browse through my channel and you'll be able to find in the quantum mechanics playlist a dedicated video on this experiment. Okay, now the first part of this question is simply asking us to draw the straight line of best fit on the figure and to determine the gradient of this line for 2 marks. Okay, well, let's do this. Okay folks, so you can see that I've drawn my line of best fit. Notice that I have a roughly equal split of data points on either side of the graph. So I have 1 point over here on the right and about 1 point over here on the left, and I just about go through a little bit of the other point. But I'm generally quite happy with my line of best fit, and I just need to determine the gradient. Remember, our golden rule for determining gradients on the exam is to make sure that our gradient triangles are sufficiently large, such as this one over here, and I've already started my gradient calculation. Remember, this is equal to change in y over change in x. In other words, y2 minus y1. My first y coordinate is, sorry, my final y coordinate is 4 minus my initial y coordinate, which is 0.4, divided by my final x coordinate, which is over here, 2.76, and my initial x coordinate is an easy one, which is 0. If I put that into a scientific calculator, I'm going to get 1.30. So in this case, we're working up to two significant figures, so 1.3 times 10 to the power of 6. It's really important not to forget the powers over here. So 10 times 10 to the power of minus 6. So let's just write that down into the answer box. So be 1.3 times 10 to the power of minus 6. Okay, let's move on to the next part. Okay, so for part 2 on the next page, it says use your answer from the previous part and the equation on page 20 to determine a value for Planck's constant to two significant figures. Show your working. Okay, let's do this. So we have our value for the gradient. Let's perform y equals mx plus c analysis. So the equation is that v naught is equal to hc over e times 1 over lambda. Now if we just compare it to y equals mx plus c, like so, I'm going to add a plus 0 because we can add that to any expression without altering it. We have v naught on the y-axis over here. We have 1 over lambda on the x-axis. Our intercept is sort of around 0, but not quite. There's probably some systematic errors that we're going to be looking at later on. But importantly, what's left for our gradient is hc over e. This over here is our gradient. So this is really, really important. So our gradient, let's call that, well, that's m is equal to hc over e. Luckily for us, we've just found this value in the previous question for the gradient, which is 1.3 times 10 to the power of minus 6. So we can go ahead and calculate h because we know the speed of light and we know the elementary charge. So h will be equal to our gradient m times e divided by the speed of light. So our gradient is 1.3 times 10 to the power of minus 6. That's what we found out. That's what our value of m is, times the elementary charge, which is 1.6 times 10 to the power of minus 19. I'm going to divide that by the speed of light c, which is equal to 3.0 times 10 to the 8 meters per second. And if I punch these numbers into my calculator, I'm going to get a value of h which is equal to 6.9 times 10 to the power of minus 34 joule seconds. Okay, next part, calculate the percentage difference between your value and the accepted value of Planck's constant. So we're just going to use the value which is given in our formula booklet. Remember, the formula for percentage difference is that this is equal to your value minus the real value, like so, divided by the real value, and that's times 100. So our value is 6.9 times 10 to the power of minus 34. The standardized value, which is given in our formula booklet, is equal to 6.63 times 10 to the power of minus 34. And we're going to need to divide that by the real value, which is, once again, 6.63 times 10 to the power of minus 34 times 100. And our percentage difference will be about 4%. In this case, we're up to two significant figures, so that would be 4.1%, which is not bad. Okay, well, the final part, identify the two types of errors shown by the data in figure 20.1 and suggest how you could have refined the experiment to reduce or to eliminate those errors. Okay, well, let's first of all start off with just identifying the two types of errors. So number one, because this whole graph is shifted upwards, that means that there would have been a systematic error. We know that because the y-intercept should be 0, but it's not. So I'm just going to write this over here, that there is definitely a systematic error. Systematic error as the intercept is not 0, as the y-intercept is not 0. Remember, systematic error means that all of those values were consistently a little bit higher than predicted by exactly the same amount. So maybe one of our instruments was not reading quite so accurately, and that affected all of our readings, and that is what actually changed the y-intercept. Now, additionally, there would have been some random errors. We can see that by the various scatter of the points, and this is what will actually affect the gradient. So the systematic errors will not affect the gradient, however, the random errors will affect the gradient. So we can say over here that there were also some random errors. So random errors, and we know that because we can say that the points are scattered. Points are scattered around the line of best fit. Around the line of best fit, like so. Now, the way we can eliminate or try to eliminate random errors would be to take many more readings and then find the actual mean. So we can just write this down. So we can say repeat readings for the potential difference. So that'd be V0 and find the mean. That will be to reduce the random errors. Now, if the room was not sufficiently dark, maybe we could have, maybe the moment in which the LED lights up would have been missed by a very similar amount by the students performing this experiment. One trick that we can use for this experiment would be to use a tube over the LED to view it when it is actually lit. So I'm just going to say that we're going to use a tube over the LED to take readings. To reduce the systematic error. Okay, let's have a go at the next one. Okay, folks, so let's have a look at the next one, which is the famous gold leaf experiment. So figure 20.2 shows a gold leaf electroscope with a clean zinc plate. The zinc plate and the gold leaf are given a negative charge by briefly connecting to the zinc plate to the negative electrode of a power supply. The gold leaf is fully diverged. The position of the leaf is not affected by intense white light. So intense white light. However, the gold leaf collapses very quickly when low intensity ultraviolet radiation from a mercury lamp is incident on the zinc plate. Explain these observations in terms of photons. Okay, let's do this. The first really important factor in explaining the following observations is the fact that the energy of the photons of the white light is definitely less than the work function of the zinc. I mean, the gold leaf is not collapsing, which means that no photoelectrons are escaping it. However, as soon as we switch to an ultraviolet radiation, the energy of the photons of the UV light is greater than the work function. It's really important to specify that here we're talking about the energy of the individual photons as well, because there is a one-to-one interaction between a photon and a photoelectron. So there's a one-to-one interaction between electrons and photons. So once an electron is ejected by a UV photon, because the energy of the UV photon is greater than the work function of the metal plate, the zinc plate, then the gold leaf will lose some charge and it will start to collapse. So we can say over here that the collapse of the gold leaf is due to loss of charge when electrons are ejected. Another final point, even though those 4 points will definitely score you full marks, but just to revise, and that's really important, is that intensity has nothing to do with energy. It has nothing to do with the energy of an individual photon. So this is really important. The energy of an individual photon is independent of its intensity. So the intensity in this case simply refers to the number of photons. Okay, well, let's have a go at the next one. Okay, let's have a look at question 21, all about magnetic flux linkage. We have a graph of B in milliteslas against the time in milliseconds. Notice that I've underlined those prefixes just in case when we use them in calculations later on in the question, we need to not forget that we need to include the factor of 10 to the power of -3. Okay, explain why the EMF induced across the ends of the coil is at maximum at a time when B is equal to 0. Well, this is the time at B is equal to 0 where the gradient is at its steepest. So right here is where the gradient will actually be at its steepest. So, and remember, the gradient is actually equal to delta B over delta T in this case. In other words, Faraday's law says that the induced EMF is proportional to the rate of change of magnetic flux linkage, like so, over delta T. So in this case, this quantity here will be the greatest at B is equal to 0, just over here. So let's just write this down. So right at the time the gradient will be greatest, and the rate of change of B as well. Okay, let's have a look at the rest of the question. Okay, for part 2 we need to draw a tangent to the curve in figure 21.2 and then use that to determine the maximum amount of EMF. So we need to carefully align our ruler with this line over here and then produce a tangent curve, like so. Now let's see if we can find the gradient of this tangent curve. Okay folks, now you can see I've drawn my gradient triangle of the tangent over here, and I've got my gradient calculation over here, and I have negative 12 for my gradient. Now I can use Faraday's law, which is that the induced EMF is equal to minus n delta BA over delta T. Now this quantity over here, this is my gradient, and I know my number of coils or number of turns, and I know the cross-sectional area. We need to be careful because that's given in centimeters squared, so I'm going to need to make sure to convert that to meters squared. Okay, well this is going to be equal to minus n, which is 85, multiplied by my gradient, which is delta B over delta T, which is minus 12, multiplied by the cross-sectional area, which is going to be 14 times 10 to the power of minus 4. Remember, when we convert centimeter squared to meter squared, what I normally do is I'll just say centimeter squared. The square acts on the centi parts as well, so it's going to be 14 10 to the power of minus 2 meters, all of it squared. You multiply out the powers, which is going to be 14 times 10 to the power of minus 4 meters squared. So it was just a quick lesson on how to convert centimeter squared to meter squared in case we're forgotten. But anyways, we put that into a calculator. Let's see what we get. We get 1.428 volts of induced EMF, rounded up to 1.4 volts for the maximum EMF. Okay, well, let's have a look at the next one. Figure 21.3 shows the variation of the EMF induced across the coil with time t. So the magnitude of the magnetic flux density is now halved. Okay, so B decreases by a factor of a half, and the coil is rotated at twice the previous frequency. Okay, so the frequency of rotation, essentially the time period, will be increasing by a factor of 2. So our time will be increasing by a factor of 2. Sketch the new variation of the EMF induced with time t. Okay, well, first of all, our EMF should not change. The reason for that is because our peak EMF will be equal to NBA cos theta divided by delta t, like so. And if our B decreases by a factor of 2 and our delta t increases by a factor of 2, the peak EMF will be unchanged, like so. However, our time period is going to be decreasing by half. So whereas before time period was 20 milliseconds, it will now be, our new time period will now be 10 milliseconds. So let's sketch that. And we can see that over here, notice that the time period has decreased by a factor of a half. However, the amplitude is the same. So I'm just going to show you that the time period is sort of contained within 10 milliseconds, whereas before it was 20 milliseconds. So 1 mark will go for the fact that the amplitude is unchanged, and 1 mark for the fact that the time period will halve. Okay, well, let's have a look at the next one. Okay, question 22, which is all about capacitors. We have a graph over here for a capacitor that a student has built, and we have a graph of the natural log of the potential difference across it against time. Show that the magnitude of the gradient of the line is equal to 1 over CR. Okay, well, let's start off with writing our basic capacitor equation, which is that the potential difference will be decreasing exponentially as it's discharging, so that's going to be equal to the initial voltage times e to the minus t over CR. And what I'm going to do then is just take the natural log of both sides, so ln of v is going to be equal to the ln of v naught. Let's just write that properly. So ln of v naught times e to the power of minus t over CR. Now, because of the properties of logs, this will be equal to ln of v, and will be equal to ln of v naught plus ln of e to the minus t over CR. And what I'm going to do is I'm just going to swap those over. So ln of v, you're going to see y in a minute, will be equal to ln of e to the minus t over CR plus ln of v naught. And now I can essentially eliminate the exponential, because remember, the natural log and the exponential are inverse functions. So what I'm going to have over here is just minus t over CR plus the natural log of v naught. Well, notice that if we compare that with the equation of a straight line, y is equal to mx plus c, in this case we have the natural log of v on the y-axis, like so. We have t on the x-axis, like so. So that's t on the x-axis, which means that our intercept will have to be equal to ln of the initial voltage, like so. So this will be our intercept. And what we have left for our gradient, so our gradient m, let's just be quite clear here and just say that our gradient m, that is going to equal to minus 1 over CR. So the magnitude of that is equal to 1 over CR. So the magnitude is equal to 1 over CR. Okay, let's have a look at the next 6-mark question. Okay, part B, use the figure to determine the capacitance C of the capacitor. Once again, I'm just going to underline just to make sure that I don't actually miss anything of the 6-mark question. Describe how the student, so I'm also going to need to describe how the student can then use the value of C to determine the value for the permittivity of paper. New description, mention any additional measurements required on this capacitor. Okay, well, because we have a figure and we know that the gradient of that will be equal to 1 over CR, we can just calculate the gradient. Okay folks, now you can see my gradient calculation over here. My gradient is equal to delta y over delta x. I've paid attention to the fact that the units on the x-axis are in milliseconds. We need to multiply this by 10 to the power of minus 3, and I have minus 87.5 for the gradient. Now, as we discovered in the previous question, our gradient, which is minus 87.5, is going to equal to minus 1 over CR. So all I need to do really is rearrange for C, also keeping in mind that R is given in the question to be 1 mega ohm. Okay, well, let's just rearrange for C first of all, and let's do that over here. C will be minus 1 over 87.5 times R. Now, as I said though, R is given to be 1 mega ohm, which is 10 to the power of 6. So what I can do is directly calculate the capacitance C. If I put that in a scientific calculator, keeping in mind that the two minus signs are going to cancel each other, and what I'm going to get is 1.1 times 10 to the power of minus 8 farads for the capacitance of this capacitor. Now for the next part, describe how the student can then use this value of C to determine the value for the permittivity. Well, our basic equation for a parallel plate capacitor tells us that the capacitance is equal to the permittivity times the cross-sectional area times, or the area of overlap really, and then divided by the thickness of the capacitor. So we can just literally rearrange this equation for the permittivity to find this out. We know the capacitance because we calculated that in the previous part of this question, so we're going to need to measure the area and the thickness of the capacitor. Now we can measure the area with a ruler. The capacitor will be sufficiently large for this normally, so we can say over here that we can measure with a ruler the area. Let's be more specific, the area with a ruler, like so. However, the thickness D, because it's just paper that we're talking about here, will most likely need to use a micrometer or a micrometer screw gauge or a vernier caliper to measure something which is quite very thin. So we can say over here that we can measure the thickness D with a micrometer, and just to ensure that we're taking an accurate reading with anytime we use a micrometer, what we're going to do is to take several readings along the length and then calculate the mean. Once we have all of these readings and we have C, so we've calculated C, we've measured D, and we've measured A as well, then what we can simply do is calculate E using the fact that the epsilon, the permittivity, is CD over A. Okay folks, so let's have a look at the next one, which is question 23 about Rutherford's alpha particle scattering experiment. And let's have a look at, in particular, the first question. It says, show that the number of alpha particles scattered through 15 degrees about 4,000 times more than those scattered through 150 degrees. Now, just as a reminder, because over here on the right hand side of this column we have the log, so LG, this is log base 10. So in order to find what n is, what we need to do is we need to raise both sides to the power of 10, and raising this to the power of 10 is actually the inverse function, so it just leaves us n, which was going to be equal to 10 to the power of 1.5. Now similarly, in order to find n for this column over here, this is going to be in this case n will be equal to 10 to the power of 5.1. So in order to show that the number of alpha particles scattered through 15 degrees is 4,000 times more than those scattered at 150, we just need to do that ratio, and this will be 10 to the power of 5.1 divided by 10 to the power of 1.5, and if we put this into a calculator we get 3,981, which is approximately equal to 4,000, so it's about 4,000. Okay, now part 2 is asking us to use this evidence from the table to explain the structure of the atom. Now, the vast majority of the particles went straight through the gold sheet, and this is indicated by the angle of 0, having a number of particles which is too large. So the vast majority of the particles went through undeflected, and we can write this in. So as we said, most particles had a deflection angle of 0, so therefore the atom must be empty space. Additionally, some of the particles were scattered at angles of over 90 degrees, so there must be a nucleus. So the vast majority go through the gold sheet. However, a few of them do get scattered at large angles, and this is evidence for the existence of a nucleus. Additionally, we also know that this nucleus must be positive because they're repelling the positive alpha particles. So we can just write this in, that the nucleus is positive, or must be positive, because it's repelling the positive alpha particles. Okay, let's have a look at the next one. A proton with kinetic energy of 0.5 MeV is traveling directly towards a stationary nucleus in a head-on collision. Explain what happens to the electrical energy of the proton nucleus system. Okay, well, in this case, because the so we have a proton over here, which is making a close approach directly towards a stationary cobalt 59 nucleus. So let's say that this over here is the nucleus. Because they're both positive, the proton is positive and this one here is positive, they're actually repelling. So as it's approaching, it's slowing down, and as it's slowing down, kinetic energy is being converted to electric potential energy. So we can say over here that the kinetic energy of the proton is being converted to potential energy. Next one, calculate the minimum distance r between the proton and the cobalt nucleus. Okay, well, this happens when all of the kinetic energy has been converted to electrical potential energy. So essentially this happens when, let's say, the proton reaches some distance as a proton, and it can no longer go any further. In this case, all of its kinetic energy has been converted to electrical potential energy, and afterwards it will be deflected. So in this case, the kinetic energy, let's call it Ke, is going to be equal to the electrical potential energy. Let's call it EP in this case. So I'm going to say that the kinetic energy is going to equal to Q1 Q2 over 4 pi epsilon naught r, where r is the distance between the proton and the nucleus. Okay, so all I need to do then is just rearrange for r. So r will be equal to Q1 Q2 over 4 pi epsilon naught, and then I'm going to be dividing by the kinetic energy now. Okay, so I'm ready to plug in some numbers to find out my minimum distance r. So let's see, the charge of a proton, that's going to be Q1, that's equal to 1.6 times 10 to the power of minus 19 times the charge of the cobalt nucleus. Now we can see that this here will have a proton number of 27. So that's going to be 27 times 1.6 times 10 to the power of minus 19 over here. And we're going to divide that by 4 pi times epsilon naught, which is the permittivity of free space, which is 8.85 times 10 to the power of minus 12, and we're going to need to multiply that by the kinetic energy. Now this is given in mega electron volts, so it's going to be 0.52, and remember mega stands for 10 to the power of 6, and then we're going to need to convert the EV to V, so I'm going to multiply by the elementary charge once again, which is 1.6 times 10 to the power of minus 19. Okay, and I'm ready to calculate my R now. And if I put all of these values into a scientific calculator up to 2 significant figures, I'm going to get 7.5 multiplied by 10 to the power of minus 14 meters. Okay, let's do the next one. Okay guys, so question 24. An isotope of polonium first decays into an isotope of lead, and then this lead isotope then decays into a stable isotope of bismuth. Figures 24 shows two arrows on a neutron number n against the proton number z to illustrate these two decays. Complete the nuclear decay equations for the first one. Okay, so if we have a polonium which is turned into this next element over here, we can see that it differs by 2 protons and differs by 4 nucleons above. So 213 minus 209 is going to give us 4. So whatever we have over here is going to have 4 nucleons and 2 protons, and this of course is an alpha particle, which is just the nucleus of helium. Okay, for the next one, the decay into the lead isotope. Now in this case, we can see that the neutron is going to turn into a proton, and it's increasing the proton number up here. This is the process known as beta minus decay, and in this case, because the proton turns into a neutron, the nucleon number remains unchanged, so this will be 209. The beta minus decay is also accompanied by an antineutrino, so antineutrino, which is normally given this symbol over here. Okay folks, so let's have a look at part B. Briefly describe and explain an experiment that can be carried out to confirm the beta minus radiation emitted from the lead nuclei. So we need to make sure that the radiation coming out of it is indeed beta minus. Now probably the easiest way would be to use an electric field, so we can use an electric field. And if the radiation is beta minus particles, in other words electrons, they will deflect towards the positive terminal. In other words, it will be something like this. Let's say that this one here is the negative one. Let's say this over here is the positive one. If the particles enter an electric field, they're going to start deflecting in this direction over here. Okay, let's have a look at the next one. Okay, the first thing we need to do in this case would be to just use this equation from our formula sheet, and remember, if we know our half-life, we know our decay constant, and vice versa. That's because they multiply together, they would give the natural log of 2. Okay, so we know our half-life, so I'm just going to rearrange for lambda, which is our decay constant. This is going to equal to 1 of 2 divided by our half-life, which is 3.3 hours. So that's 3.3 times 3,600, like so. And if we put that into a calculator, we get our value of the decay constant to be 5.8345. So let's say 5.835 times 10 to the power of minus 5 for our decay constant. Now that we have our decay constant, we can work out our final number of particles. So I'm just going to use that the activity is equal to the number multiplied by the decay constant. We now know what our decay constant is, and which is just over here as well, and we know that our initial activity is 12 kilobecquerel, so we can just work out n. So n will just be equal to A divided by lambda, n, in other words, is going to be 12 times 10 to the power of 3 divided by this number that we just found for lambda, which is 5.835 times 10 to the power of minus 5, like so. And this is equal to a very large number as expected for the number of particles, which is going to be 2.57 times 10 to the power of 8 particles. Okay, perfect. Now we can work out the initial number of the lead nuclei just using the exponential equation that n is going to equal to n naught e to the minus lambda t. Now in this equation we know our number of particles, final number of particles n, that's over here. We know what our lambda is, and we know that the time is 7 hours. So all we need to do is just rearrange for our initial number, which is the last part of this question. So n naught is going to be equal to n over e to the minus lambda t, like so. So this will be equal to 2.057 times 10 to the power of 8 divided by e to the minus 5.835 times 10 to the power of minus 5 multiplied by 7 hours, which is going to be 7.0 times times 60 minutes times 60 seconds, so 3,600. And let's put that into a calculator, leading us to an answer of 8.95 times 10 to the power of 8 particles. Okay folks, so question 25, the last question. The nuclear reaction below shows how the isotope of fluorine 18 is made from the isotope of oxygen. Okay, explain why a high-speed proton is necessary to trigger the nuclear reaction shown above. So we have a high-speed proton which collides with this nucleus over here, producing fluorine and a neutron plus a gamma ray. Well, we'll need a high-speed proton because the proton is otherwise repelled by the nucleus. So the high-speed proton is normally repelled by the nucleus, but a high-speed proton has sufficient kinetic energy to reach close to the nucleus. Just as we did on question 23, we have that conversion from kinetic to electrical potential energy, and we can actually calculate the distance of closest approach. In general, the more kinetic energy we have, the closer the proton is going to get. Okay, so for the next one, we need to estimate the minimum wavelength of the gamma ray photon. In the previous part of the question, we're given the fact that initially the oxygen nucleus is stationary, but the proton has kinetic energy of 0.25 times 10 to the power of minus 11, and the binding energy of the oxygen is 2.24 times 10 to the power of minus 11, and we're given the binding energy of the fluorine nucleus, which is 2.2 times 10 to the power of minus 11. Now the following question is all about energy conservation. In fact, what has happened is that the energy of the proton has turned into some binding energy. So we can just summarize that with just as a little diagram here to illustrate the kinetic energy of the proton has gone into some difference in energy plus the energy of the gamma ray. Now let's first of all work out the difference in energy. So we can work this one out fairly easily, because initially the binding energy was equal to the 2.24 times 10 to the power of minus 11, and later on after the collision it was 2.2 times 10 to the power of minus 11. That was the binding energy of the fluorine. So minus 2.20 times 10 to the power of minus 11, which is going to give us a delta E of 0.04 times 10 to the power of minus 11 joules, like so. So now we can work out directly the energy of the gamma ray photon. Let's call that E gamma ray actually. So the energy of the gamma ray photon is going to be equal to the kinetic energy of the proton minus the change of energy which we just found. So the energy of the proton was 0.25 times 10 to the power of minus 11, and then from that we're going to take away 0.04 times 10 to the power of minus 11, which is going to give us 0.21 times 10 to the power of minus 11 joules. Now, after we have that, we have the energy of the gamma ray photon, so we can just use that E is equal to hc over lambda to work out the energy, to work out the wavelength of the gamma photon. So lambda will be hc over this energy of the gamma photon, and Planck's constant will be 6.63 times 10 to the power of minus 34 multiplied by the speed of light, which is 3.0 times 10 to the 8. We're going to divide that by 0.21 times 10 to the power of minus 11, and we're going to get a value for the wavelength of 9.5 times 10 to the power of minus 14 meters. And a little bit more of the medical physics to finish off this paper. Fluorine-80 is a positron emitter. Name a medical imaging technique that uses fluorine-80. Well, this is PET scans. So PET scans, and state one benefit of this technique. Now the PET scans, they can produce 3D images. So they can produce 3D images. And the very last question of this paper, describe how the components of the CAT scanner can be used to produce high quality images of the internal structures of the patient. So let's get started. So with the CAT scanner, an X-ray tube is moved around the patient. Now the X-ray tube will then be producing a thin fan-shaped X-ray beam. It's thin because it's needed to produce high quality, high resolution images of the internal structures, and the cross-sectional images of the internal structures are produced, and those can be put together to form a 3D image. Okay folks, so hopefully solving this paper you guys have found useful. If there are any questions, feel free to drop a comment down below. Thank you very much for watching.